So at this point in your journey through complex analysis on the integration side, you should have two big integration theorems in your mind. One is Cauchy's integral theorem and his generalized integral theorem, which allows you to compute integrals when you can write your integral as integral some analytic function f of z, z minus z naught to some power. So when you can do that, then you can use Cauchy's integral theorem. And then now we have this new result, which is known as Cauchy's residue theorem. And so let's just try it out. So here I want to integrate over the circle, the unit circle with positive orientation. We already found the residue of this function above. If you remember, let's scroll back up actually. I hope this doesn't make you too seasick here. Scroll up. Oh, and we got the residue to be minus 1 over 6. So instantly, I know the value of this integral is 2 pi I times minus 1 over 6, which is what? Minus pi I over 3. So that's just wonderful. And what's nice about it is a lot of times, not always, a lot of times it's not that difficult to compute the Lorentz series of a given expression, particularly when you can work from known series like we could here. So that integral was just a piece of cake, and we got it. Let's go on to another integral. I want to work out this example with you two different ways. So first, let's work this integral out using Cauchy's residue theorem, because that's what we're trying to learn. Then let's go back and work it out with Cauchy's integral theorem. And I'll let you decide which one is faster in this case. I'll warn you now, we're not saying the residue theorem is always better. It's just another tool in your toolbox which you can use when you see fit. So let's have a look at this. And I want to realize, first off, that this function, when I'm looking at this circle centered at 2 of radius 1, when I'm looking at this particular function, 1 over z, z minus 2 to the 4th, it's analytic not just inside the circle that I want, it's analytic on this deleted neighborhood of 2 all the way out to this circle here. So this is the circle centered at 2 with radius 1, 2. Does that make sense? My function is analytic on this deleted neighborhood of 2 with radius 2. We're interested in the curve of radius 1 living inside there. And so instantly, because I'm analytic all the way out here, I know that this integral is going to just be not just the residue of f of z, it's going to be 2 pi I times the residue at z equals 2 of f of z. So it all comes down to finding the residue. Now in this case, I don't necessarily have this Lorentz series for this function worked out, so I'm going to have to develop that from scratch. And so let's work through it together. So I know that 1 over 1 minus z, my starting series is just the geometric series. I'm going to start with this. And I know that this is valid for what? Modulus of z less than 1. And so I thought it would be good to work through the steps on how one would find the series here. I know you guys have just done a lot of that in the homework, but let's do another one together. So I'm interested in centering my series around 2, which means this z minus 2 to the 4th, I'm going to factor that out. That's already as a power of z minus 2. That's what I want. I can multiply that in later. It's this 1 over z that I've got to deal with. So I'm going to write this as 1 over z minus 2 to the 4th, and then I'm going to say times 1 over 2 plus z minus 2. And if you notice, that's just 1 over z. I haven't really changed anything. And now I say, okay, well, to write this, to make use of the geometric series, I need a 1 sitting here. So I'm going to pull a 2 out, and I can write this now as 1 over 2 z minus 2 to the 4th. I'm left with 1 over 1 plus z minus 2 over 2. I'm going to actually erase the plus and write this as minus, minus, and we'll do that. And now I'm ready to roll. So this is equal to 1 over 2 z minus 2 to the fourth. And I actually can go ahead and switch to my series. Series n equals 0 to infinity. Whatever's inside here. So minus 1. And by the way, I wrote this poorly. That negative there, I mean like not on the z, I mean in front of it like that. There we go. That was a rookie mistake there. So minus 1 to the n, and then I'm going to have what? Z minus 2 to the n over 2 to the n. All right, so that's where I'm at so far. I should remind myself when this is valid. This is valid for z minus 2 over 2 modulus less than 1, and then we already said, hey, that's got to be bigger than 0, which is the same as saying z minus 2 less than 2. So that's where this is valid for. And now I just need to clean it up a little bit. I'm just looking for the residue. So if you wanted, you could just write out some terms. It's not about manipulating this to the nth degree. It's kind of a pun. It's really about finding the residue. But I'm going to go ahead and combine it just for the sake of completeness. So I'm going to get minus 1 to the n. I'm going to get what? Z minus 2 to the n minus 4. And then I'm going to have 2 to the n plus 1. And that is my Lorentz series. And now you can write the terms out if you want to. If you wanted to go starting at n equals 0, you're going to get a negative 4 power on the z minus 2. I'm just going to look for the residue at this point. And so I can see that when n equals 3, that's going to give me the residue. When n equals 3, I get minus 1 to the third is negative z minus 2 to the minus 1 over 2 to the fourth. And so that tells me now that the residue at z equals 2 of f of z is just negative 1 over 16. And so the integral that I want, the integral over c of 1 over z minus 2 to the fourth dz is 2 pi I times the residue, negative 1 over 16, which is just negative pi I over 8. Now, that took a little bit of work to find the Lorentz series, and I'm going to show you another way to solve it. And here we're just going to use Cauchy's generalized integral formula. So let's think about it together. So I'm going to think about this integral as the integral over c of 1 over z minus 2 to the fourth dz. And I'll think about this now as, just to be clear, 1 over z minus 2, I'm going to write it as 3 plus 1. And the reason that I'm doing that is because I want to make sure that we see what our n is. N is 3. And so from Cauchy's integral formula, you know that this is exactly 2 pi I over 3 factorial times the third derivative of my function g. I haven't told you what g is, evaluated at 2, where, let's go in purple, this function is my g of z. And this works as long as this g of z is analytic on and inside c, which it is. So now I just have to take the third derivative. I don't want to spend too much of your time doing that, but I'll just point out to you that the g prime of z is negative 1 over z squared. G double prime of z is what? 2 over z cubed. And the third derivative of g is what? Negative 6 over z to the fourth. So this is going to be 2 pi I over 6 times minus 6. Plug in 2 to the fourth. Cancel the 6's, pop out the negative, cancel the 2's, and you get exactly what we got before, minus pi I over 8. Now, in this case, at least looking at the length of our work, Cauchy's integral theorem was faster. And so I'm not telling you that Cauchy's residue theorem is always faster. However, we're going to develop some techniques which will allow us to get our hands on the residue without having to compute the entire Lorentz series. So that's where we're going, is Really, the residue theorem is quite nice if you can compute the residue efficiently. And so that's our next goal in the next lecture series. I'm going to go ahead and give you guys some homework. I'll tell you in the video and write it down, but then I'll post it online as well. I would like you to look at the problems from page 239. If you could please do number 1 and number 2. And let's make these due on Tuesday. Oh boy. I'll have to look at my calendar real quick. Tuesday. Stalling. Tuesday, April 21st. And then I'm going to assign you some more homework that Friday. So there'll be more homework due on Friday, the 24th. And then we'll have probably one more assignment after that, the last week of classes. I haven't decided what I'm going to do for a final, but I'll be in touch with you when I do decide that. All right. Ciao.